Hello, I'm Mirko, and in this video I'll give you a brief overview of PLAMS, our Python library for building workflows and automating molecular simulations. In your research, you probably have to run many molecular simulations to obtain the chemical or physical insight you are after. You might have to run a sequence of calculations, or you might have to run many similar calculations, or perhaps many similar sequences of calculations. In such situations, it might be possible to automate the procedure using our Python library PLAMS. All the main engines of the Amsterdam modeling suite can be used in combination with PLAMS, and your workflows can combine different engines. PLAMS is a Python library, which means you need to be somewhat familiar with the Python language in order to use it. If you don't know Python but would like to learn it, there is a huge amount of material online to help you getting started. But even if you're not familiar with Python, you can still follow this video and get a taste of what PLAMS is about, and it will hopefully stimulate you to learn more about it. In this video, I'll guide you through a PLAMS Python script implementing a simple example workflow consisting of the following steps. First, starting from a smile string, we will generate 50 conformers of some molecule. Then, we will optimize the geometry of all the conformers using the semi-empirical engine dftb. Out of the 50 conformers we optimized, we will then select the one with the lowest energy, and we will perform a single point DFT calculation for it and extract the bond energy and HOMO-LUMO gap. Doing all of this manually can be quite human labor intensive, especially if the same procedure needs to be performed for several different systems. But using PLAMS, this workflow can be easily automated, potentially saving you a lot of tedious work. My goal here is to give you a general idea of how PLAMS works and to mention the most important components and concepts in PLAMS. I won't go too much into the details, and I will often refer you to the PLAMS user manual, where you will find more detailed explanations and several examples. So let's dig in and let's go through the script. The first step is to generate the 50 initial conformers. We can do this by using the fromSmiles function that takes as input a smile string and optionally the number of conformers to be generated. The fromSmiles function returns a list of molecule objects. The molecule class is an important component of PLAMS as it contains the geometry of the system. For example, in this snippet you can see how one can create a molecule object from an XYZ file, guess the bonds and print it. Although the name might suggest otherwise, the molecule class can also deal with periodic systems such as crystals or 2D slabs. Now that we have generated our 50 initial conformers, we can go to the next step of the workflow, that is to optimize these conformers with a computationally fast engine dftb. Here, we specify the settings for the geometry optimization with dftb. We set the AMS driver task to geometry optimization, and we set the details of the dftb calculations. The settings for the calculations are specified in a settings object. The settings class is another important component of PLAMS. There is quite a lot to say about the settings class, and I would strongly recommend you to read more about it in the PLAMS manual. For now, all you need to know is that the settings class is used to specify the input options for the molecular modeling engines, and that the various input options are described in the user manual of the corresponding engine. Next, we create an empty list where we will store our results. We are now ready to set up and run the dftb geometry optimization. We loop over all the conformers, and for each conformer we create a new AMS job using the settings we just defined. We then run the job by calling the run method and append the results of the calculation to our list of results. The AMS job class handles calculation with the programs of the Amsterdam modeling suite. This is another very important class of PLAMS, and a lot could be said about it, but I will once more point you to the PLAMS manual for more details. The next step in the workflow is to select the conformer with the lowest energy. Here, we loop over all results of the previous geometry optimization, looking for the conformer with the lowest energy. In PLAMS, the results of the simulation can be accessed via the results class. You can see here how to use the getEnergy method to extract the energy of the optimized molecule and the getMainMolecule method to extract the optimized geometry. You can also extract results directly from the binary KF file using the readRKF method, and you can even extract results from the text output of the simulation using the grepOutput method. Let's move to the final step in our workflow, that is to perform a single point calculation using DFT for the conformer with the lowest energy. Here we define in a settings object the input option of our DFT calculation with band. We set the AMS driver task to single point and set the exchange correlation functional for band to PBE. We then create a new AMS job using as molecule the conformer with the lowest energy and using the settings for band we just defined. And then we call the run method to run the job. Like before, we use the getEnergy method to extract the energy. We then use the readRKF method to get the homolumo gap from the binary KF results file. Here, band structure is the name of the section of the KF file we want to read from, and band gap is the name of the variable. File equals engine indicates that this should be read from the engine results file, which in this case should be the band.rkf file. Finally, we print the results we just extracted. See how we use the units class to perform the unit conversion from Hartree to electron volt. Okay, we covered the whole script. Now it is time to actually run it. Let's save it as workflow.py. You can actually download the script from a link in the description below and start up a terminal. To use PLAMS, you should make sure that the AMS environment variables are properly set. To test this, you can type $adfbin/plams-h and you should see the PLAMS help message like you see here. If the AMS environment variables are not set, you should source the adf-bashrc.sh file in your ADF home installation folder. So to run our script with PLAMS, we type $adfbin/plams and the name of the script, workflow.py, and hit enter. As you can see, PLAMS logs the progress of the simulations as they run. Let's wait for the calculation to finish. It should take just a couple of minutes depending on your hardware. At the end, we can see the results of the calculation we printed, that is, the geometry of the conformer, its bond energy as computed by band, and the homolumo gap. When you run PLAMS, a folder called PLAMS workdir will automatically be created. Inside it, you will find one folder for each job that was executed, and inside that, the input and output of the actual AMS calculations. Okay, this concludes my brief introduction to PLAMS. I hope I gave you an idea of how PLAMS can help you to streamline and automate your simulations. It might take a bit of effort to learn how to use PLAMS, but it can really be a huge return on investment. If you're interested in learning more about PLAMS, I would recommend you to check out the user documentation and examples on the SAM website. You will find links to this in the description. Thank you for your attention and take care.